Okay, let's take a look at the valve subassembly. It is a pretty simple assembly. It's only made up of three parts. First one you can see in green is the valve, and then up top here we have outside is the retainer in black, and then inside we have the valve spring retainer, which is in gray. It is a very simple assembly. It only uses 4 total mates. For the valve spring retainer, it is concentric with the cylindrical face in there, we will see later in the individual part. And then it's also coincident with those two faces. That's just to restrict motion and keep it in that spot. And then for the retainer, it is also concentric with the valve spring retainer inside. And then it is coincident with those two faces also to restrict motion, just to have the valve spring retainer inside of the retainer. So now let's take a look at the parts that make up this assembly. So first here we have the retainer. It is, if we look at the sketch here, it has sort of like a bowl shape with a section in the middle for the valve spring retainer to be mated into, as we saw in the assembly. And it has sort of an odd geometry, but that's to account for the valve spring retainer, which would fit into this section here. And it's just used, or it's made using a revolved extrude, as you can see here, about this center line. Now we'll look at the valve spring retainer, which is very similar to the retainer, but with much less complex geometry. If we look at the sketch here, it is just essentially a rectangle that widens as it goes up, and then it is also revolved around this center line, which allows it to fit into the retainer in the assembly. And the last part we have to look at is the valve, which is the most complex part in the subassembly, but it's still nothing too crazy. Looking at the sketch here, it's made on the right plane. It's essentially just a rectangular L shape with a bit cut out of it right here to make this cylindrical section, which the valve spring retainer will be mated into. And then other than that, it just uses a fillet here at the bottom to round out this edge, and it also has a chamfer, which you can see at this angle, and it has one more chamfer up at the top to round off this edge. And those are all the parts for the valve subassembly.
Hello, Brendan M. Chinick. How is it going? Today we're going to talk about my parts, the parts that I made, the internal parts. The poison for Cusco. Cusco's poison. First up, we got our little valve. That's what opens and closes to let, well, that's what it says there. Air and fuel in and gases out. They kind of, there's two of them. Like, we made one, duplicated it, and they kind of go at different times. But for this one, I kind of just sketched the outline you see, and then extruded it in like a circle. And then I just used the fillet tool for most of it, to kind of just get all like the round edges I wanted. On the top, I did one cut extrude at the top to get like that weird little shape you see. But that was the only like specialty type thing that I had to do. Wait, no, that wasn't for this part. That was for another part. On this part, yeah, it's all just fillets and little rounded things. The next one was the spur gear. This is actually the one I made first because I like how it looks. There's probably a million better ways I could have done this, but I made a circle first, and then I drew on one of the on the I built it on the right plane. I drew a circle, and then I drew out the like spokes on the edge, is or at least one of them, and then I just rotated it across, and I think I put like 36 of them. Um, but that's how I got that bit. Then for the rest, I used in the middle thing. I just made that shape and then cut extruded it, and then I cut it extruded, not cut extruded. I just regular extruded from the mid plane out, that little intersection, and then the rest of it, like that, those holes, I cut extruded those, and that little dip that you see in the middle, not the middle, but like, the kind of side middle. I cut extruded that in as well. And that's how I made that bad boy. Then for the shaft, this was the second easiest. All I really did was make a long shaft, fillet on both sides. And wait, no, hold up. It wasn't a fillet. It was a different tool. I can't remember what it was, but it kind of just made them round. No, hold up. It was a fillet. I think I used like a radius of 17 or something like that. And then that for that little bit that's kind of in the middle, I just made that as like a circle, extruded it into a cylinder, and offset it. And that's how I got that little thing. For the piston pin, this was by far the easiest. I just made a circle, extruded it out into a cylinder. Then in the middle, I drew another cylinder on that face or circle, and then I cut extruded that through so I got like a little hole through. That's how I made that little housing for the piston pin. Um, Super easy, barely an inconvenience. Then the rod, this one honestly probably took me the longest. Um, I just made that circle shape for the cylinder at the bottom. Then I made the longer cylinder, and I extruded first the short cylinder, then the long cylinder off of the short cylinder. Then on the bottom, I think I filleted that circle to get it to look like that little round thing. And then on top, I filleted that to the longer line. Then on the top, I made another little circle and I pulled it out, making a wider thing. Then this is the one that I kind of had a complex thing on. Um, I made that shape that you see, and I extruded it off of a mid plane that was on the right plane, I think. Um, and then I made a bigger circle around this circle that you see, and did a cut extrude up to make sure that the corners were pretty rounded. And then I filleted that thing to be pretty round too. And that's how I made my parts.
So the first part I designed was the piston. To create the overall shape, I started by sketching the 2D cross-section of the piston on the right plane, and I used the revolved boss base feature to revolve it 360 degrees around the chosen center line. This generated the full cylindrical body you can see in the pictures on the current slide. The circular hole through the middle of the piston that connects to the connecting rod was created by sketching a circle and then extruding through all. The piston skirt at the bottom was created using a center point arc as well as the spline tool, which was then extruded throughout the entirety of the piston. The next part I designed was the connecting rod, both the body and the cover, which together form the connecting rod subassembly. For both parts, I created the shape by drawing a detailed sketch of each part's profile and then extruding it to the desired thickness. To fully create the bore region at the small end and the big end, I used offset entities, which allowed me to accurately offset the circular geometry inward, which allows me to properly defines the wall thickness. Fillets and chamfers were applied both parts all throughout to round edges and corners, and also just make it more structurally sound. For the crankshaft, this is the most complex part I designed. I began by sketching the crank web profile, which includes the counterweight shape, and extruded it to create the first crank web. The main journal and crank nose were then made by sketching circles on the face of the crank web and extruding them outward as cylindrical bosses. The journal was also extruded from the crank web face at the correct distance. Once one full side of this design of the once one full side of the geometry was finished, I used the mirror feature to mirror it around the right plane. A keyway slot was then added at the end of the journal. A big challenge for this design, the crankshaft specifically, was just defining it properly.
Hi, my name is Isaiah Commander, and in this section of our project, I'll be going over the engine assembly and the motion study that I created using SolidWorks. To start, my main responsibility was to take all the individual parts that my group members have designed and combine them into one complete SolidWorks assembly, which is displayed in these images below. And after this section, I have a 30-second video that shows a motion study of the engine rotating at 20 RPMs. Every part that you can see in these final models came from different members of my group. So my job was to bring everything together and make sure it all aligned correctly. To assemble the engine, I used a variety of mates. The basic ones, which was coincident, concentric, some tangent mates. And in the photo, if you look hard enough, I used some sketches and I added a plane in to help me align the models. This all helped me to line up the surfaces, center holes, and make curved parts touch properly. For the moving components, I use more advanced mates like the cam mate and the gear mate. These mechanical mates are what allowed the parts to interact realistically and rotate together the way that an actual engine would operate. While I was putting the assembly together, I also added a few reference features to help with alignment, which was the sketches and the planes and added axes. These references made it easier to fully define the model and ensure that all the parts were placed exactly where they needed to be. Once the structure was fully aligned, I applied a gear mate to synchronize the rotation between the gears. This means that when one gear spins, the other automatically spins with it, just like in a real mechanical system. And in order to create the gear mate, you have to take the count of one teeth and then the other teeth. So then that way when it spins, it interacts correctly. After the assembly was complete, I created the motion study for it to show how an engine would operate. I added a motor set to 20 RPM and ran the simulation for 20 seconds. This motion study lets the entire assembly rotate smoothly at a constant speed, and it demonstrates the basic rotational motion of the engine. Overall, the assembly required a combination of basic mates, mechanical mates, and reference features to get everything aligned and moving correctly. With all of these tools, I was able to create a clean and fully defined model that shows how the parts work together as a system. To wrap up my section, the next slide includes a 30-second video of the motion study so you can see the engine rotating in real time. And with that, it should wrap up our entire presentation. And with that, it wraps up our full presentation. Thank you for listening.